In this video, we're going to do a modeling and similitude example. So in this example, we are considering an elliptical bridge column. And this elliptical bridge column looks like this. So we have an ellipse with some diameter, semi-diameter D, and long ways diameter H. And this bridge column is exposed to wind at some velocity, and that wind velocity is 50 kilometers per hour. So we have an elliptical bridge column which sheds regular vortices and these vortices look like this, right? So we have the flow coming past it. We have some vortex which comes off like this. Maybe we have another one that looks like this, and then previously shed vortices might look like this. We have this train of vortices, and this regular vortex pattern can impose this rhythmic sort of force profile on your bridge, and that can create damage to the bridge. So this can create harmful forces on the structure. So we're given a wind velocity. So this is the wind velocity that this bridge would experience out in the field. We said this was 50 kilometers per hour, which I'll just make a note here that that's equal to 13.9 meters per second. So for this particular wind velocity and for dimensions, we have dimensions of D is equal to 0.1 meters, and H is 0.3 meters. So we're given the wind velocity, we're given the dimensions of this bridge column. So this is the cross-section that I've drawn for a diameter D of 0.1 meters and a length H of 0.3 meters. We want to find the vortex shedding frequency. So in other words, what is the frequency at which these vortices are being created and being sort of ejected or shed into the wake of this bridge column? Now to do this, we're going to use a small scale model in a water tunnel. So we're looking at wind, right? But instead of using a wind tunnel, we're actually going to use a water tunnel. So we're using water as a working fluid instead of air in our model system. And so we're given some dimensions here. So we're D sub m. So the D of the model is equal to 20 millimeters. And then we're also given some properties of the different fluids that we're working with. So we know that the viscosity of air is 1.79 times 10 to the negative 5 kilograms per meter second. The viscosity of water, though, is 1.00 times 10 to the negative 3 kilograms per meter second. So we're using a different working fluid. And we know the density of air is equal to 1.23 kilograms per meter cubed, whereas the density of water is, we'll say in this case, 998 kilograms per meter cubed. So here in our prototype, which is the original system, we have air as our working fluid, which has these given viscosities and this given density. And then in our model system, we're doing it in a small-scale water tunnel and using water. And water is, of course, 1,000 times more dense than air and has a different viscosity as well. And so dimensional analysis and modeling and similitude allows us to work in a different fluid for our model setup. And so we are asked to, first off, to find m and the velocity that we need for the model. So we were given d sub m right here, but we're not given h sub m. So the first thing we need to do is to find that. So first off, we are going to we have to do a dimensional analysis to figure out what our model system to our prototype. So we're going to do dimensional analysis. And so the dependent variable that we're trying to learn more about is this the shedding frequency, omega. And this is a function of all of the other variables that we have listed here. So it's a function of d, the diameter, h, which is the length, our velocity, v, the density of the fluid, and the viscosity of the fluid. So here we have our different parameters, and now we can go ahead and list the dimensions of those parameters. So frequency is 1 over time. This is a function of d. The diameter has a dimension of length. The h variable has a dimension of length as well. Velocity, of course, has a dimension of length over time. Density here, we're going to use the mass length time system. So we're going to say mass over length cubed for density. And then for the viscosity, we have mass per length time. Okay, so we have our dimensions listed here, and we can then apply the Buckingham pi theorem to say that, well, we have 6 different variables, right? We have our one dependent variable, and then we have 1, 2, 3, 4, 5 independent variables. So we have a total of 6 variables in our system, and then we used 3 different dimensions to describe those, right? We used t right here, we used l right here, and we used m right here. So we have 3 different dimensions that we use to describe the system. So we have 6 minus 3, and that tells us that there's going to be 3 different pi groups here. So at this point, we could find our pi groups using the method of repeating variables. I'm going to, in the interest of time, do this by inspection, and you can see this in section 7.5. This is a technique that you can use when you have some more experience with this type of system, and you can kind of recognize what groups of variables are important because they tend to show up again and again. So in this case, we would see that we have some variable that involves, or some pi group that involves the frequency, and we know that frequency is 1 over t, and we multiply that by d, and then divide that through by velocity, and we end up with a dimensionless group here. We can do something similar, but we're going to see that we're going to need to have a variable that just involves two lengths. So this length scale, so we have length over length, and that is a dimensionless group as well. And then the Reynolds number is of course going to be important here as well, rho VD over mu. And of course, in this case, we have, so we have mass over length cubed. We have length over time, and we have length here as well, divided through by mass, divided by length times time, and this ends up canceling out as well to be 1. Now, if you're not familiar or comfortable using this method of inspection, which I haven't really gotten into in detail here, you can read more about that. You can certainly use the method of repeating variables and get the exact same solution. So the next step then is going to be to write out this relationship. We have omega d over v is a function of d over h and rho vd over mu. And because I've been doing this for a while, I recognize that this grouping is a kind of Struhal number, and this is a Reynolds number right here. So this is our relationship among our variables. Okay, now the second step here is to say that if we want to keep similarity between our model and our prototype, then that means both of our both of these groups here need to be similar. So to keep similarity, between the model and prototype, we would say that d sub m of the, so that's d of the model, divided by h sub m, so that's the h dimension of the model, is equal to d over h for the prototype as well. So that's our first restraint to say that in order to keep similarity. And secondly, we would say that rho of the model times v of the model times d of the model over mu of the model is equal to rho vd over mu of the prototype. So both of these both of these equations have to hold in order to keep similarity between the model and the prototype. Now, we were asked to find a value for h sub m right here. The dimension, the sort of length dimension of this elliptical bridge column. And this relationship here gives us a way to do this. So we can say straight off the bat that h sub m is equal to d sub m over d times h. And so here we can say that we know what d sub m is. We were given this in the problem, that this is equal to 20 millimeters, so that's 0.02 meters. So this is equal to 0.02 meters. And then dividing through by d, which is the dimension of the actual prototype, the actual system, so that's 0.1 meters. And we multiply that by h, so that's 0.3 meters. And we find that h sub m, so this dimension of our model, must equal to 0.06 meters. And so that maintains similarity, in this case, geometric similarity between the model and the prototype. Now, how about this second equation here? So in the second equation, we're equating the Reynolds number, rho vd over mu, of the model to the Reynolds number of the prototype. And we need to find the velocity of v sub m, so the velocity that's going to be used for the model. And that's what we were asked for up here. We want to find the velocity of the test model. Okay, so we're going to solve this equation for v sub m. And it's usually helpful to sort of group your like parameters together, and that's what I'm going to do here. So I'm going to say mu of the model divided by mu of the prototype times rho of the prototype divided by rho of the model times d of the prototype divided by d of the model, and all of that times v, and that's the v belonging to the prototype. Okay, so we're going to take that equation, we're going to scoot down here and plug in some values here, because we actually know we know our values for mu sub m and mu of the prototype. We know our values for the densities. We know the different dimensions and the sizes of d, and we know what v is in the real world. So we know all of these values, and so we're going to start to plug in here. So we have to say that v sub m is equal to mu sub m. So this is 1 times 10 to the negative 3 kilograms per meter second. That is the viscosity of water divided by the viscosity of air. So 1.79 times 10 to the negative 5, again, kilograms per meter second. So that's the ratio of the viscosity used for the model divided by the viscosity of the prototype. So water divided by air. Multiplied by 1.23 kilograms per meter cubed. So this is the density of the fluid used for the prototype. For the prototype, we have air, so that's 1.23 kilograms per meter cubed, divided by the density of the fluid used in the model system. So that's our water tunnel. So that's using the density of water. And then we have D, so capital D right here, of our prototype, which is the original system. So that's 0.1 meters. And we were given as part of the problem that D of the model is 0.02 meters. And finally, we have V. So V is 13.9 meters per second, and that's the speed of the wind, which is the speed of the flow in the prototype. So we can then calculate this, and we'll find a value of 4.79 meters per second. So we would need to use a flow speed of 4.79 meters per second for the water in our water tunnel in order to keep similarity with our prototype. Okay, so the third part of the problem here says that if the model shedding frequency, so if we go out and we do experiments with the model and we measure the frequency of these vortices being shed from the model, and if we do those experiments and we find that we measure a vortex shedding frequency of 49.9 hertz, then we want to find the prototype shedding frequency. And this was the goal all along, was to find what is the frequency of the shedding of these vortices on this large-scale system, original system. And so to do this, we now return back to our relationship here. So what we've done, we've equated this variable, we've equated this variable. We know that those two are similar, and because of that, we know that the dependent variable is also going to be similar. And so what we can do now is we can say, okay, omega d over v of the prototype is equal to omega of the model times d of the model divided by v of the model. And we want to know what omega is for the prototype, that is for the original system. So we have this relationship. We can rearrange to solve for omega. And so we see that this is equal to this ratio of dm over d times this ratio of v over vm times omega of the model. So now we can plug in values here. So omega is equal to dm, which is the diameter of the model, which was given to us, divided by the diameter of the real thing, the prototype. Now we have the ratio of the velocity that we used, or the velocity that the prototype experiences out in the field, divided by the velocity that the model experiences in our water tunnel, then multiplied by 49.9 hertz, which is the shedding frequency that we measured in our small-scale model system. So we calculate that, and we find that omega is equal to 29 hertz. So this is the frequency that we would find if we went out into the field and measured the vortex shedding frequency on the large-scale, real, original elliptical bridge column out in the field. But again, by doing experiments in on a smaller system and on a model system, we can figure this out much more cheaply and faster than going out and doing measurements on the actual large-scale system itself.